Advanced Algebra 2, solve linear systems by graphing. So a system of two linear equations is two or more equations that have two variables. Typically it's x and y. So they're usually written in standard form. They don't have to be, but that's just typically how you see these equations. In standard form is what you see there in your notes packet and on the screen. So ax plus by equals c, and then a second equation, dx plus ey equals f. And that's where the coefficients a, b, c, d, e, f are constants. So this is standard form. But basically what you're trying to find is the solution, if there is one, to the system. And the solution is the ordered pair, the one point, or it can be many points, where those lines cross. It can also be no points if the lines are parallel. So let's try a problem. When you solve by graphing, you want to just get it in a form and get some points. So one easy way to do that is to put your equation in slope-intercept form. Now I'm going to be pausing the video and doing some work. So when I say pause the video, you may want to and do the work on your own and then start it up so you can catch up. So go ahead and solve each of those equations for y. First of all, pause the video, solve for y, and then come back and we'll graph. So when you solve each of those for y, you'll end up with y equals negative 4x plus 8, so a slope of negative 4 over 1, a b value of 8, and then the second equation you'll get y equals positive 2/3 x minus 6. So to graph, remember you're going to have a straight edge when you actually draw your line, but start with your equation on the left with your y-intercept, which is 8. So we'll plot 8 right on the y-axis. And then the slope is negative 4 over 1, so I put the negative with the numerator, so that means we'll go down 4 and over 1 to the right. Just check and make sure that you're creating points with a negative slope. So as you look at it left to right, they are decreasing. Alright, then you use a straight edge. I'm not able to on this. Fill up your graph space with your line. Now let's graph the second line. So notice our y-intercept is negative 6, and then our slope is positive 2 over 3. So that's up 2 and over 3. And as you do that, we can see the point where they intersect. And I'm going to capture that point. So that is at negative 3. I'm looking here. Sorry, positive 3, negative 4. Alright, I'm going to go ahead and finish drawing my line. But that's what we're looking for. So the point or points where those lines intersect. And again, remember, make your lines with the straight edge. And then they'll be very accurate. So they'll cross right where they need to. Okay, look down at the bottom of the page of your notes. So we're going to classify these systems if the system has a solution. So like the first two graphs. So either one solution or many solutions, infinitely many, where they graph as one line, then we call them consistent. And then distinguishing between those two is if the two lines are separate, they intersect at a point, then they're independent. That makes sense. Then if they're not, if they graph right on top of each other, then they are dependent. And then finally, if a system has no solution, the lines are parallel, then they are called an inconsistent. And we don't go on with the second. Independent or dependent is only for consistent systems. So now as we solve systems, we're going to label them either as consistent or inconsistent. And then if they are consistent, we'll label them as independent, so they cross at a single point, or dependent. So looking at the next example in your notes, it does say solve a system with many solutions. So you'll see what they look like when they graph. So the first thing we do is we want to give them in graphable form. So let's just start by putting them in slope-intercept form. So pause the video, do that for both of your equations, and then come back and check your work. Now at first glance with the system, they look like two separate lines, two separate equations, but when you solve them, you see that they have the same slope and the same y-intercept. So when you graph them, they are virtually going to graph right on top of each other. So they will have infinitely many solutions. Now when you graph this, we're graphing a b value that is negative 8/3. So my first suggestion would be to change that to a mixed number. So that would be negative 2 and 2/3. So you put your first point there. I'm going to graph in purple since blue and red make purple. So we'll go negative 1, 2 and 2/3. So about 2/3 of the way. Now from there I'm going to count up 4 and over 3. So I'm going to stay 2/3 of the way each time I move up. 1, 2, 3, 4, 1, 2, 3. And I'll do that again. 1, 2, 3, 4 up and 1, 2, 3. And then I'll go ahead and draw my line. I want to fill up my graph space. Yours will be a lot straighter than mine. But virtually, we would have one line graphed right on top of each other. So there are infinitely many points where those two lines are crossing. Let's try this again. And there we go. Many solutions is how we say it. So because it does have a solution, it is a consistent system. But since we can't distinguish those two lines, then we call it also a dependent system. Oh, sorry, that's my dog. The next system is what a graph of a system looks like with no solution. So you can imagine that they're going to be parallel lines. So go ahead and pause the video, solve each for y, go ahead and graph them, and then come back and check your work. So when you graph it, well, first of all, when you solve for y, notice that your slopes are the same, but your y-intercepts are different. So that's going to create a situation with parallel lines. So we've got parallel lines that will never cross. So that is no solution. And because they don't have a solution, then we call them an inconsistent system. Now we're going to talk about systems of inequalities. So see how our problem has changed. We have a linear inequality, which means we've got two variables, x and y, and rather than an equal sign, it's an inequality. So when we graph it, we're going to have a range rather than just a solid line. So the solution of a system of inequalities is one solution would be an ordered pair, but what we do on a graph is we show the whole, what we call solution region or solution area. And we do that by shading. So this is where you would want to have two different colored pencils so that you can shade. Now I put kind of steps on how to do that, but basically you're going to graph the inequality very similar to how you graph a line. You'll just need to remember that you have to show if you have a situation where it is equal or not equal. So if you have an inequality that's greater than or less than, so it's not equal to, then you're going to use a dashed line. If you do have the equals sign underneath, so greater than or equal to, less than or equal to, then you'll use a solid line. Then you're going to shade according to the inequality. So in y equals mx plus b form. So if you have y is less than or equal to mx plus b, then you're going to shade below, or depending on how the line is slanting, to the left. If you have a greater than or equal to, then you want the area that is above. or depending if the line is upright, then to the right. You can always test a point in your inequalities to see which side or which part of the lines to shade. But getting a little ahead of ourselves, so let's look at those two inequalities. They're already in slope-intercept form, so let's start and graph the first. Our y-intercept is at -5. And I'm going to graph this one in blue. So I'll put a little blue dot there. So my first point's at -5, and then I'm going to go down 2 and over 1, and I'm going to do that a few times. I can also go up 2 and then 1 to the left. Okay, then what I want to do is notice my inequality is just greater than. So I'm going to dash that line through those points. I want to show everything that is greater than that line. So I've got now my graph space divided into two areas. We call them half planes. So this line is slanting, so I want the half plane that is greater than. So I'm going to shade with my yellow highlighter, and this is going to show everything that's greater than that line. So you can do that with one of your colored pencils. Now the second line I'm going to graph in red. So I'm going to put a point at +3, and then my slope is just 1 over 1, so there's always an understood 1 there. I can make it into a fraction. So I can just go up 1 and over 1. And then that inequality sign is less than or equal to. So I'm going to draw a solid line. And I want to show everything that's less than. So since my line is slanted, then I am going to shade below my line. Now our solution region, so it's an entire area, is the double shaded area. So that is just in here. And that shading kind of covered up my blue line. So that's my solution region. So with these problems, your graph is the answer to the problem. You can draw an arrow and show that double shaded area, but it's not the area with the single shading, it's the one that's double. So if you picked any point out of that area or on the solid line, that would satisfy both of those inequalities. So if we pick 0, 0, because that's in our solution region, and we plug it in, so underneath where I say test a point, I'm going to plug 0 into my first inequality, and I'll get 0 is greater than -2 times 0, which is 0 minus 5. And that's true. 0 is greater than -5. And then if I plug it into my second one, 0 is less than or equal to 0 plus 3, and that's also true. So right there, that's how you solve a linear inequality by graphing. You actually graph the two inequalities and you shade, and then you just indicate the double shaded region. Number 5 is a system of inequalities with no solution. So pause the video and then solve for y on that top inequality, graph them both with the shading, and then come back and check your work. So when you graph those inequalities, you've got parallel lines, and then with the way that the inequalities are, you're going to shade below your first line that's dashed. You'll shade above your second line, so there is no area that is overlapped. There's no double shaded region, so that there's not going to be any of that area that will satisfy both. So that will be a no solution inequality system. This next system has an absolute value with a linear inequality. So it's a constant inequality. You simply go to where y is 3 and you're going to draw a straight, solid line through. Now I haven't shaded yet so that you could see that shading together. So we're going to shade underneath because we want everything that's less than 3. Now I've gone ahead and graphed my absolute value. So I noticed just from what we studied before that that's going to shift 4 to the left. So that's going to move my vertex to -4, 0. Nothing else has been transformed, so it'll simply go up 1 and over 1 in both directions. I want everything that's greater than that absolute value. So that means I'm going to shade, oops, let's try this one, above it, and in this case it's inside. So my double shaded area is in this small overlapping region here. So that's my solution region. I could pick any point out of that area and it would work for both of my inequalities. So let's say I pick the point 1, 2, 3, -4, +2. So if I come over here, I'll plug in my y value, which is 2, and so 2 definitely is less than or equal to 3. And then here I'll say 2 is greater than my absolute value of -4 + 4. So 2 is greater than 0. I could also pick any point on the line, so, but I could not pick a point that's on the dashed absolute value graph because that would not satisfy both of them. Now finally let's look at example 7, which is solving a real-life inequality situation. So you can work at most 20 hours next week. You need to earn at least $92 to cover your weekly expenses. Your dog walking job pays $7.50 per hour, and your job at the car wash pays $6 per hour, a little less than what you would probably make now. Write a system of linear inequalities to model the situation. So the first thing is we're going to talk about kind of the two variables, things that are changing in this situation. So one of them is the hours that you work for your dog walking, and then hours for the car wash. So hours for dog walking and then hours for car wash. And then we'll write any qualities for those situations. So let's just call them X and Y. And then we have two different situations where we can write our inequalities. So one talks about our hours and one talks about the money. So our total hours that we can work is 20 at the most. So we would say that our hours for the dog walking plus the car washing can be at the most. So it has to be less than or equal to 20. Now we need to earn, though, $92. We make $7.50 per hour for the dog walking here, and then we make $6 for the car wash. And together those need to be greater than or equal to 92. Now to graph this, we know that we're not going to go into the negatives. So we've talked about this before in a real life situation. So let's make an L-shaped graph so we don't need to waste any of our graph space with negatives. And then let's use the technique of X and Y intercepts to find. So we're going to think of these as equations for a moment. And then the X and Y intercept is just where they cross those axes. So if I plug in 0 for X, Y is going to give me 20. If I plug in 0 for y, x is 20. So that gives me 2 points. That's all I need to know to graph a line. Now if I go to my other inequality, so 7.5x plus 6y, and we'll just think of it as an equation for a moment. So if you plug in 0 for x, then you'll just take 92 and divide it by 6. And I believe that is 15.3. If I plug in 0 for y, then I'll have 7.5x equals 92. So I'll just take 92, divide it by 7.5, which is 12.3. So here's what it looks like graphing those two lines. My y values only go up to 20, so I can just go ahead and have this by ones. So this would be 5 and 5. So my first point will be 0, 20, and then 20, 0. It can be equal to, so I'm going to draw a solid line. And then if I put this in slope-intercept, I see that it's less than. So I'm going to shade everything that's less than this line. So I'm going to shade underneath. Alright, my second line, and I'm going to graph that in red. I've got the point 0, 15 and a third. So about right there. And then 12, 5, 10, 12 and a third, 0. And that can also be equal to, so I have a solid line. But I need that to be greater than. So if I go over here and I solve this, 6, let's try that with our red. So 6y is greater than or equal to negative 7.5x. And then y is greater than or equal to x plus. But what I'm looking at is the sign, so that's going to help me know where to shade. So now with this line, I'm going to shade above. So what I get then is this double shaded area right in this middle strip. And in that area are all my combinations of hours of dog walking and car washing that will give me the situation, that I need, where I'll be working at the most 20 hours, but earning at least $92. So right in that area is our solution region.